In this video, I will be presenting an overview of frequency response. In steady state, sinusoidal inputs to a linear system generate sinusoidal responses of the same frequency. Although these responses are of the same frequency as the input, they differ in amplitude and phase angle from the input. These differences are a function of frequency. Since the system causes both the amplitude and phase angle of the input to be changed, we think of the system itself as represented by a complex number, defined so that the product of the input phasor and the system function yields the phasor representation of the output. If we observe the transfer function of a sinusoidal frequency response, we call m of omega the magnitude frequency response and phi of omega the phase response. The combination of the magnitude and phase frequency response is called the frequency response. We define the magnitude frequency response to be the ratio of the output sinusoid's magnitude to the input sinusoid's magnitude. The phase response is the difference in phase angle between the output and the input sinusoids. We also want to note that the magnitude of the sinusoidal output is equal to the magnitude of the sinusoidal input multiplied by the magnitude of the system's frequency response. The phase of the sinusoidal output is equal to the phase of the sinusoidal input plus the phase of the system's frequency response. If we want to analytically express the transfer function of a system, for example g of s as a frequency response g of j omega, we substitute s equals j omega, express the frequency response into real and imaginary parts, and find the magnitude and phase of the frequency response. Let's look at an example of how to find the frequency response from a transfer function. In this example, we want to find the analytical expression for the magnitude and phase frequency response for g of s. G of s is equal to 1 divided by s plus 6. So the first thing we want to do is set s equals j omega, and this would then give us the frequency response g of j omega equals to 1 divided by j omega plus 6. Then we want to find the magnitude frequency response analytical expression, which is equal to 1 divided by the square root of omega squared plus 36. Next, we want to find the phase frequency response analytical expression, and this is equal to the negative tan inverse of omega divided by 6. Frequency response can be plotted in two ways. First, as a function of frequency, with separate magnitude and phase plots referred to as Bode plots, and second, as a polar plot, where the phasor length is the magnitude and the phasor angle is the phase. When using Bode plots, the magnitude can be plotted in decibels versus log of the frequency, where the decibel value is equal to 20 times the logarithmic of the magnitude. The phase curve is plotted as a phase angle versus the logarithmic of the frequency. Now let's look at an example of how we would want to plot the frequency response. Using the same example, g of s equals 1 divided by s plus 6, we're able to solve for the analytical expressions for the magnitude and phase frequency response. So if we choose an omega equals to 1 radians per second, then we would expect our magnitude value to be minus 15.68 dB and our phase value to be minus 9.46 degrees. To plot the frequency response for the function g of s, we first create the linear time invariant transfer object. Next, we use the Bode command to generate the magnitude and phase plot. Once the Bode plot has been generated, we want to find the value for the magnitude response and phase response at 1 radians per second. So at 1 radians per second, we can see that we're getting minus 9.5. Our original calculation was minus 9.46 degrees. And for the magnitude response, we're getting a minus 15.7 dB, and our original calculation was minus 15.68 dB. So these results correlate with our calculation. In conclusion, this video presented an overview of frequency response, finding frequency response from a transfer function, and plotting frequency response using Bode plots with the MATLAB control system toolbox. If you've enjoyed this video, please like, comment, subscribe, and share this video, and I'll see you in the next video.